Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds, space expanded exponentially, growing much larger in size. After this period, space continued to expand, but at a much slower rate, eventually leading to the universe we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. However, a few physicists believe this premier theory doesn't paint an accurate picture of the universe's evolution. They suggest that the universe existed before the Big Bang, stretching forever into the past and future. While the universe is expanding today, it was contracting before the Big Bang, and this contraction reversed into expansion, not as a bang but as a bounce. According to their theory, the universe could bounce again, with today's expansion potentially followed by a collapse in the far future and another bounce. Some physicists suggest this bouncing could be infinite. This, of course, counters the view of most cosmologists, who believe everything started with the Big Bang. However, it's noteworthy that this is not the only theory challenging the pinnacle of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding to the debate, the James Webb telescope has made unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise the question, if the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe have started with a bounce or something else entirely? Join us as we dig deep into one of the thorniest issues in physics. The idea that the universe had a beginning, known as a day without a yesterday, dates back to Georges Lemaitre in 1927. Although it's still defensible to state that the universe likely had a beginning, that stage of our cosmic history has little to do with the hot Big Bang that described our early universe. Although many laypersons and even some professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is outdated. The Big Bang is no longer seen as the birth of time and space, a fact we know today in 2023. In fact, there's a ton of evidence pointing to a non-singular origin of our universe. We never reached those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang, with the Big Bang as the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty, no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time by about 1 part in 30,000 on average. As the universe inflated, expanding rapidly, those fluctuations got stretched to larger scales, while new small-scale fluctuations were created atop them. This superposition of fluctuations at small, intermediate, and large scales is a defining feature of cosmic inflation. This continues as long as inflation goes on, but inflation will end randomly and not in all locations at once. If you lived in an inflating universe, you might experience a nearby region where inflation ended, while the space between you and it expanded exponentially. For a brief instant, you might even detect what happens at the start of a Big Bang before that region disappears entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball but possibly much larger, the energy inherent to space converts into matter and radiation. This conversion process is relatively fast, taking about 10 to the power of -33 seconds, a brief amount of time, but not instantaneous. As the energy bound up in space converts into particles, antiparticles, photons, and more, the temperature rapidly rises from just a few degrees above absolute zero to perhaps 10 to the power of 20 Kelvin over the same brief interval. Because the amount of energy converted is so large, everything moves close to the speed of light. All quanta behave as radiation, with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. This conversion process, known as reheating, signifies when inflation ends and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior. When the hot Big Bang first commences in an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly. But when inflation ends, the universe reheats, and the hot Big Bang starts. More distant regions now recede from you more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain time, and once that time elapses, the distance doubles again, and again, and again. The process is relentless. But once the Big Bang begins, all of that changes as the expanding universe immediately slows down. Once the first moment of expansion elapses, it's extremely likely that, from the perspective of whatever region of inflating space you're in, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, expanding more slowly than the still inflating regions, leaving you in the inflating region as a typical region within spacetime, dominating its volume. These regions where hot Big Bangs occur will expand away from all other locations where inflation still goes on exponentially, meaning they will quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we live gets cosmically lucky, and inflation ends for us. The energy inherent to space itself converts to a hot, dense, and almost uniform sea of particles. The only imperfections and departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions, but that's still enough to serve as the seeds of cosmic structure. We cannot observe these density fluctuations as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even so, we can extrapolate back to what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations imprinted on the first picture of the universe, the cosmic microwave background, confirm how the Big Bang began. However, there are many inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting as we think it should. Second, light from the cosmic microwave background is lensed by matter between us and it, meaning that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem that it's sometimes called a crisis for cosmology. Third, the two hemispheres of the cosmic microwave background sky have different average temperatures.